Last time we talked about the Fibonacci sequence, and I briefly mentioned at the end of the video that a golden ratio is something closely related to the sequence. So today we'll be talking about, drumroll please, the golden ratio. Now I think all of us have heard the term golden ratio more or less as we grow up. When you look at ancient Greek statues, people will tell you they're constructed based on a golden ratio. Same with a lot of human portraits, because somehow they make people look prettier. But how? What is the golden ratio anyways? Well, it is an irrational number that we often know as 1.618.0339888 blah 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 with endless decimals to come. But its exact expression is actually 1 plus root 5 over 2. It's often denoted as phi. Note that this phi is different from the phi in Euler's-Tolshan theorem. To learn more about that phi, check out our previous video. The mathematical history of the golden ratio dates back to the ancient Greece, where Euclid introduced it in the context of geometry around 300 BCE. The ratio became prominent in arts and architecture during the classical period. In the Middle Ages, Fibonacci's sequence revealed a connection between the golden ratio and natural growth patterns, which we'll discuss in details later. Then during the Renaissance, mathematician Luca Pacioli collaborated with Leonardo da Vinci to explore the mathematical and artistic aspects of the ratio. The quadratic formula devised in the 19th century also solidifies people's understanding about the ratio. Mathematicians nowadays still research the ratio's connection to number theory. Yes, the number theory that brings us tons of pain. Now, let's derive the ratios ourselves. If the ratio of two numbers is the same as the ratio of their sum to the larger of the two quantities, the two numbers are mathematically defined to be in golden ratio. To express it algebraically, we say a plus b over a equals a over b equals phi. In order to calculate phi, we first simplify the fraction. A plus b over a simply equals to a over a plus b over a. Since phi is a over a, intuitively we know b over a can be expressed as 1 over phi. So a over a plus b over a equals 1 plus 1 over phi. We multiply both sides by phi and get phi plus 1 equals phi squared, which can be rearranged into phi squared minus phi minus 1 equals 0. Then we can use the quadratic formulas to solve for phi, and we get 1 plus root 5 over 2 and 1 minus root 5 over 2. Since phi is a ratio between positive quantities, phi is necessarily a positive root. So we take the positive number, 1 plus root 5 over 2. Great, that's our golden ratio. Pretty easy, right? Well, let's look at a cooler way of deriving it, using the Fibonacci sequence. If you don't remember what the Fibonacci sequence is, it is a sequence that can be expressed recursively as fn equals fn minus 1 plus fn minus 2. Each term is the sum of the two previous terms. It starts with f0 equals 0 and f1 equals 1. So the sequence goes 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, etc., etc. Now, let's observe the sequence. If you divide 34 by 21, 21 by 13, or 13 by 8, or any term by its previous terms, you'll find that the ratio is always around 1.62. Therefore, we conclude that the numbers actually increase exponentially, which means the term fn can be expressed as something to the power of n. Let's set this something, the base, to r. So fn equals r to the power of n. Since fn equals fn minus 1 plus fn minus 2, r to the power of n equals r to the power of n minus 1 plus r to the power of n minus 2. We want to find r, so let's try to get rid of n. We divide each term by r to the power of n and get 1 equals r to the power of negative 1 plus r to the power of negative 2. We don't like negative exponents because they're kind of ugly to calculate. So let's multiply each term by r squared. Then we get r squared equals r plus 1, since r to the power of 0 is just 1. We rearrange it to get r squared minus r minus 1 equals 0. Does this equation look familiar? Yep, it is exactly the same as phi squared minus phi minus 1 equals 0 that we get from the golden ratio's definition. If we solve it using the quadratic equation, we get 1 plus root 5 over 2 as the positive root, the golden ratio. That's really exciting, isn't it? Even a naturally occurring Fibonacci sequence follows the golden ratio. Maybe that's why it is the secret to the natural beauty. Well, that brings us to the end of our explanation of the math behind the golden ratio. It's time to dive into its real-life applications.